like to ask you all, yeah. Wednesday is going to be our midterm test, right? We have 1 hour lecture session there. So your midterm test duration is actually 1 hour. So I'm actually thinking, because I have class immediately after the Wednesday lecture, so I was thinking of starting the midterm test at 1:30. All right. Anyone got any concern? Do you have class at between 1:30 and 2 o'clock?
No, miss.
Oh, no class, huh?
No, miss.
Okay, so we're gonna start our Wednesday lecture at 1:30. So your test is gonna start at 1:30. All right. And then hopefully we can finish by of course when we start at 1:30. So I presume you need some time to actually download the questions and then work on it, and then later on I have to give you some time to upload your solution as well. So hopefully everything will finish by 3 o'clock. All right, because at 3 o'clock I have another class. Okay. So I'm gonna make a formal announcement in Google Classroom later on. Yeah, so everybody please take note, yeah. Okay, so as I mentioned previously, the scope for this midterm test is mainly on AM and FM. So make sure you have your appendix easily available, and make sure you're familiar with the AM and FM standards also. All right. And prepare maybe 3 to 4 sheets of foolscap paper for you to write your answer on. Yeah. Get your calculator accessible as well. And also make sure your camera is working. So either on your laptop or on your handphone, your camera must be working, because during the midterm test, all of you are required to turn on your camera. All right. Okay, yes. Anyone who do not turn on their camera during midterm test will not be allowed to sit for the test. So even though you may submit your solution, but I will disqualify your solution. So I will not accept your solution if you do not turn on your camera. All right. Okay, what else? So any questions on your midterm test?
Miss Scott. What is it? I got a question about the midterm test.
What is it?
About the amplitude modulation. The chapter in amplitude modulation is the summary of comparison at the last slide will be act as a reference. Can be act as a reference for the midterm test.
The last slide. What is the last slide about? Comparison, right?
Yes, summary of comparison, the Formula 1.
Oh, okay. So as far as your assessment concerned, because it's an online assessment, be it exam or be it midterm test, they are all open book. So you are allowed to refer to any material. I won't formally put it as a reference under your Google Classroom or anything, but you are free to refer to any material.
So it's an open book test.
Yeah, it's an open book test. But
Okay.
again, because the test is open book doesn't mean the answer is in the book, All right, you really need to understand the material in order to answer the question. All right, there is no such thing that you can copy bullet the answer from your book. All right, you have to digest it and you might have to rewrite it. Of course, the answer is there, but it's not in a form that you can just copy and paste. All right, so you have to again do some modification yourself. So don't wait until last minute only you study, or you think no need to study because it's open book. The reason is open book is because I can't control, because some may be so honest that they don't, if I put it as closed book, some will be so honest they don't actually refer to anything. And if some student want to refer to anything also, I won't be able to tell. All right. So I think to be fair to everybody, it's an open book test. So it's the final e-assessment, it's also open book. But again, if you refer to the past year question, the last session, the last exam session for this table, for this paper is open book. And if you compare the past year questions of the open book exam with the closed book exam, you will see that the open book exam are more difficult. The open book exam questions are more difficult because they will be open-ended. There is no one single solution. All right. Again, you might want to refer to it. Yeah. So that will give you an idea how your open book assessment will look like. Okay. Did you have a chance to go through the past year paper? Any of you went through past year paper? Okay. If you actually got a chance to refer to past year paper, the test basically the scope will be the same as your past year exam question 1 and 2 as in the closed book exam. That means the exam that actually student came into college and then sit in the exam room and for the exam. And then the open book one is the previous exam, which was held in last sem. No student visit, so that one was held somewhere in I think October or September. Last year, October and September. Okay, that was the open book exam. So that question, if you actually read the question in that exam, you will see that the style and everything is very different from the question paper on closed book exam. And I must say, the student did not do well in that exam because they expect, again, they thought open book, they'll be able to get answer from the book. Unfortunately, yeah, the answer is in the book, but you need to know where to get them, all right, and how to make use of it. All right. So again, you have to be very familiar with the course material. All right. And the only way to be familiar with it is you must actually go through it yourself and you do your revision. Okay. And also understood the tutorial solution and so on. Okay. Any other questions?
No question.
Okay. So if no questions, then I'm going to start with the lecture on chapter 5, which is pulse modulation. Okay, can you see my slides on chapter 5, pulse modulation?
Yes.
Yes.
Okay, all right, good. So the outlines for this chapter are as follow. We're going to study about pulse modulation. And before we go into details, we need to know a bit about sampling theorem. And I believe you have studied sampling theorem in your DSP. So this is not something new, or just a quick revision. Then we're going to move on to study the three types of pulse modulations. All right, the first one is pulse amplitude modulation, or PAM in short. The second one is pulse width modulation, or PWM in short. And the last one is called pulse position modulation, and PPM in short. Okay, the learning outcomes for these chapters are as follow. First one is after you've gone through this chapter, you should be able to explain, all right, explain the various pulse modulation schemes. All right, how does each pulse modulation technique works? And then you need to be able to apply Nyquist theorem in sampling. All right, then followed by calculating bandwidth requirement for PAM signals. And last but not least, explain TDM of PAM signals. TDM stands for time division multiplexing. All right, so pulse modulation, right? As I mentioned previously, pulse modulation consists of the three types, which is PAM, PWM, and PPM. So PAM, which is pulse amplitude modulation. In these modulation techniques, as the name suggests, the amplitude of the signal is proportional to the amplitude of the message signal. All right, so in a way, it's quite similar to AM. Yeah, and then for the next modulation technique, which is called pulse width modulation. So as the name suggests, the width, so it actually represents the amplitude of the message using the width of the pulse. All right, tau is the width of the pulse. And then for pulse position modulation, the position of the pulse is proportional to the amplitude of the message. All right, and the position on the pulse is actually represented by the pulse delay. All right, how much the pulse is delayed, and this is again expressed in time. Okay, these are the graphical representations of the three types of pulse modulation techniques. So the first graph here basically show you the modulating signal, or what we call the message signal, all right, in time domain. And these are our sampling points, all right, meaning we're going to read the amplitude of the modulating signal at this time. Yeah, and for pulse amplitude modulation, the pulses generated, all right, will have its amplitude, all right, at that instant of sampling. The amplitude is proportional to the amplitude of the message over here. All right, this amplitude will be proportional to the amplitude over here at the instant of sampling. Yeah, and the second instant of sampling, when the amplitude of the modulating signal is high, the pulse amplitude is high. All right, and of course, at this instant of sampling, the pulse amplitude is very small or nearly zero. Then you can see the pulse amplitude is small as well. Yeah, so for pulse amplitude modulation, the width of the pulse is constant. Pulse width is constant. Pulse location is constant as well. All right, so the pulses are generated at fixed interval. All right, and the pulse wave is fixed, but the pulse amplitude varies. All right, the pulse amplitude varies according to the amplitude of the message signal here. All right, and again, after learning the AM modulation techniques, we know that whenever the amplitude of the modulated waveform is used to represent the amplitude of the modulating signal, this kind of waveform, or this kind of signal basically is easily affected by noise. All right. especially when you have noise added to it, then your amplitude will change, right? And if the signal experience noise with negative amplitude, then again your amplitude will be reduced. So it will no longer be a true representation of the baseband or the modulating signal amplitude. So that's a problem with PAM. Then let's move on to PWM. In PWM, the width, all right, the width of the pulse, all right, is proportional to the amplitude of the modulating signal. All right, taking example, just some obvious one is if you look at this instant in time, all right, the amplitude of the modulating signal is the highest. Therefore, you can see the width of the pulse is the widest as well. Yeah. The sampling point is still the same. So at the instant of sampling, which is here, all right, the pulse will go up. All right, but how long it lasts, right, depend on the amplitude of the modulating signal. Yeah. And let's take another example here where the amplitude is the lowest. You see that at this instant of sampling, the width of the pulse is the narrowest. All right. So in PWN pulses, the pulse height now is constant. All right, the pulse height is constant throughout. The pulse location is also constant, meaning the start of the pulse. All right, the pulse actually starts at the instant of sampling. Yeah, but how long it lasts depend on the amplitude of the modulating signal. So because the information on the modulating signal is now represented in the width of the pulse, no longer in the amplitude of the pulse. So this kind of signal is less susceptible to noise as compared to PAM. Okay. Then the third type of pulse modulation techniques, which is pulse position modulation. All right, so in this one, if you actually look at the waveform carefully, the pulse height is the same throughout, all right? And the pulse width is also the same throughout. But the time when the pulse appear actually depend on the amplitude of the modulating signal. All right, let's take one example here, some obvious one. Okay, here, again, same point where the amplitude is the highest in the modulating signal. This is my sampling point. All right, so because the amplitude is the highest, so it takes a longest time for the pulse to appear. So this is the delay time. All right, so the delay is the longest because the pulse amplitude is the highest here. And if you look at another point, which is the minimum here, all right, where the amplitude of the modulating signal is the lowest, you can see that there is minimum delay or the least delay in the pulse that generated. All right. So so again, the how much the pulse is delay is proportional to the amplitude of the modulating signal. All right. So in ppm, pulse width and height are the same throughout for all the pulses, but the location changes. All right. So the location actually change according to the amplitude of the modulating signal. So again, because the information on the amplitude of the modulating signal is now actually represented by the delay time in the pulse. Therefore, it is again less susceptible to noise as compared to PAM. All right, the message is not represented by the amplitude. The message is represented by the time delay in the pulse being generated. Okay, clear on this? Clear? Or you have questions? No questions? Then I move on. All right, let's take a quick look at sampling theorem. All right. So because pulse modulation requires sampling of the modulating signal at a fixed interval, so we need to know a bit about sampling theorem. All right. So as far as sampling is concerned, we actually sample an analog signal at every, in this case, I call it TS second. All right. So what is TS? TS is the sampling interval or the sampling period. All right. So the sampling frequency is just 1 over TS. All right. And we also call it sampling rate. Yeah. So the question is, because the pulse modulation requires sampling of the modulating signal, so we need to ask ourselves, you know, how densely or how frequently should we sample the signal? All right. So that we can actually represent the signal accurately, and then we can reproduce them later on accurately as well. All right. And of course, I believe you have studied this in your DSP course, and we need to make use of Nyquist theorem. All right. And this Mr. Nyquist said the sampling rate must be at least 2 times the highest frequency contained in the signal. All right. Again, when you have a signal that consists of many frequency components, so the sampling rate must be at least 2 times the highest frequency that you have in that signal itself. All right. And then the easiest way to remember it is Fs is must be greater than or equals to 2F max. Yeah, right? F max is the maximum frequency in your analog signal or your baseband signal. Right. And of course, Nyquist also mentioned, you know, why we must sample at least 2 times, because if you don't sample at least 2 times the highest frequency, then you're going to have a liaising effect. Yeah. So the diagram on the right hand side basically show you lah. Okay, so the first diagram on the top actually show you when we perform sampling at 2 times the frequency of the baseband signal. So here we have a very simple analog signal, which is a sine wave. All right, if we actually sample at 2 times the frequency of this sine wave, meaning during each interval, we have to take 2 sampling points. All right, we have to take this 2 points here. All right, so if we actually sample at these points, all right, and 2 times the frequency of this sine wave, we will be able to get a close approximation on the analog signal here. All right, even though this is triangle, but you can say the waveform actually is very similar. Because when you do some filtering, you'll be able to recover the sine wave easily. And of course, the point of sampling is important. If you don't sample at the maximum and minimum, let's say you sample somewhere here and here, or no, or even here, you might not be able to represent the waveform correctly. Yeah. And picture B actually show you what happened when you do oversampling. All right, so in this case, we actually perform the samplings at 4 times the frequency of the sine wave. All right, so actually you take 4 points within 1 period. All right, and then from the waveform. And of course, you can see the representation again is very similar to when we sample at 2 times the frequency. All right, so in this case, there is not much benefit gain. All right, whether you do sampling at 2 times or you do sampling at 4 times. But of course, this is for single frequency signal. There is not much difference. But then for a signal that consists of many frequency components, a bit of oversampling will actually be more It will actually be helpful, all right, in creating a more accurate signals. And we'll see it later on. Okay, and then for undersampling meaning we perform the sampling at in this case the sampling frequency is the same as the frequency of the signal. All right, so that means we actually sample the signal at take 1 point. All right, such that there is only 1 point taken, 1 sample taken during the entire period of the signal. All right, so in this case, you will see that when we try to reconstruct the signal, all right, we won't be able to get the original waveform back. Okay, so I believe you have learned about all this from Dr. Yo, right? Okay, then we say that if we don't sample at 2 times the highest frequency in the signal itself, we will actually have aliasing problem. All right. So what is aliasing problem? Okay, aliasing basically is the overlap. All right, the overlap of a low frequency and high frequency components in our signal that causes distortion in the recovered signal. All right, let's take a look at this waveform here. Okay, what waveform is this? This is not a waveform. Basically, this is a spectrum. All right. So whenever we need to study the frequency behavior of a system, it's best to actually analyze them in the frequency domain. All right, and then therefore you need to look at the frequency spectrum. So in this case, I have the frequency spectrum of a sampled signal. All right, and this is actually the baseband spectrum. So when I sample the signal at the sampling frequency Fs, so what happened is in the time domain or in the frequency domain, you actually has duplicates. All right, you actually have a duplicates of the baseband spectrum centered at the multiple times of your Fs. All right, in this case, this is 1 Fs. All right, you will have a duplicate again at the 2 Fs, 3 Fs, and so on. All right, so in this spectrum, we just look at the baseband as well as the 1 Fs. Okay, so if your sampling frequency, right, is more than 2 times the bandwidth, right, in this case, it's more than 2 times the bandwidth, isn't it? All right, this is 1 bandwidth. All right, the next bandwidth is here. All right, 2W is somewhere here. So this Fs is greater than 2W. All right, so if you were to sample your signal in this way, um, you will be able to recover your baseband signal later on, okay, using a low pass filter. All right. Um, of course, this is the for the ideal low pass filter. All right. If your low pass filter is not ideal, all right, then you will not have a sharp transition here. You will have a gradual transition here. All right. So this explains why your sampling frequency must be more than 2 times the bandwidth. All right. If you sample a ngam, just nice at 2W, and then your low pass filter is not ideal, then your low pass filter will allow some of um, the first sideband or the second one on this side here, right, to actually pass through your filter. All right. So again, if this happen, then whatever you recover will not be the exact spectrum of the baseband signal. Okay, the third graph on the left hand side show you the example where your sampling frequency is less than 2 times the bandwidth of the baseband signal. All right, so if you sample at less than half of the 2 times the highest frequency in your baseband signal, you see that the spectrum, all right, the spectrum of your signal, your sampled signal will overlap. This is the overlapping here. All right. So this overlapping is the one that contribute to aliasing error. Yeah. And then later on, when you actually try to recover your baseband signal using a low pass filter, and again because your low pass filter is not ideal, well, it's ideal also you have problem. Okay, and then it's going to allow, all right, allow all these signals to come in to actually pass through the filter, and therefore whatever you recover will not be the exact version of the original one. Okay, the original one is this one, like that. Yeah. So here at these two tails on this left and right side, you will not get the original shape back. Okay, a better description on this phenomena is actually represented on the right hand graph here. Okay, and this is your baseband. Okay, this is your baseband frequency spectrum. Yeah, and this is a spectrum where we actually sampled at less than 2 times the highest frequency component in your baseband signal, or less than 2 times the bandwidth of the baseband signal. So you're going to have overlap here. All right, where the baseband spectrum is going to overlap with the spectrum that's on the, I would say, the first one. Okay, and then of course on the other side you also overlap here. Okay, so this overlapping is the one that causes aliasing error. Okay, so what is aliasing error? So again, because these two spectrum overlap, all right, so you see that the resultant, okay, the resultant waveform or the sample signal waveform, the spectrum is going to take this shape already. All right, that means the higher frequency component here, all right, the magnitude has been changed. All right, and the lower frequency component here, the amplitude has been changed as well. All right, so this will cause your signal to be distorted. The signal that you recover is not actually the original spectrum anymore. All right, so your signal will be distorted here. All right, at these two ends. And after you have recovered it with the filter, even though your filter is ideal, you know, in this case, we actually show you an ideal filter, all right, where you actually have a sharp cutoff. However, yeah, your this one, because you have a folded tails over here, overlap over here, yeah, so this amplitude has been changed. All right, and you have also lost the higher amplitude information. All right, the highest frequency over here, the information is lost because you actually block them with your filter. All right, if you don't block with your filter, you try to recover it up to this point, what will happen? All right, again, you can see the highest frequency component will be much higher than what it was originally. All right, so that was the effect of aliasing error. Okay. Okay, let's go through one example. So in this example, we have a signal called XT. This signal consists of 3 frequency components. One is 4,000 pi, one is 5,000 pi, the other one is 8,000 pi. All right. So this signal has to be truly represented by its samples. Find the minimum sampling rate for low-pass sampling theorem consideration. All right, so what is the minimum sampling rate here? So to find the minimum sampling rate, you need to know the highest frequency in the signal component, isn't it? Right or not? So what is the highest frequency here? So again, from the equation, you should be able to tell what is your frequency, right? So here, what is your frequency? F1 equals to
8,000 pi over 2.
2,000, right? 4,000 pi over 2 pi give you 2,000 hertz, isn't it? All right. And this one, what is your frequency here? 2005, right? All right. 2 pi f ma. 2 pi f is 5,000. So f is 2005. And this one here, f3 is
4,000.
equals to 4,000. Yes, 4,000 hertz. All right. So with this, what is your f max? X max is 4,000 hertz, right? Yeah. Okay. So what is my minimum sampling rate?
8K.
Yeah, very good. It's 4 kilohertz. All right, F sampling rate must be the minimum. Must be 2 times F max. So that will give you 2 times 4K, which is 8 kilohertz. All right. 8 kilohertz also means is 8,000 samples per second. All right. 8,000 samples per second. Yeah. Okay. So that's easy one. So let's move on further on the topic of pulse amplitude modulation. All right, so as far as pulse amplitude modulation, we actually sample the signal at regular intervals, yeah, and then each sample is made proportional to the amplitude of the signal at the instant of sampling, right? Remember, this is what pulse amplitude modulation is about. Right, so again, this is our original or the modulating signal, our message that we want to sample. Okay, and at the instant of sampling over here, okay, we get a pulse. And the height of this pulse is proportional to the amplitude of the message at the time when we take the sample. All right, and so these pulses are actually sent over a distance with or without modulation. All right, so if you were to send pulses like this, all right, you definitely have to send through wired. All right, send through wired, a cable. All right, you can't send pulses like this wirelessly. There's no way. If you want to send pulses like this wirelessly, you have to perform modulation. All right. So this is, and then as far as this is this pulse PM signal is concerned, because the original message signal has positive and negative amplitudes. Therefore, the PM also has positive and negative amplitudes. All right. So if your system is actually working on single polarity, all right, meaning you only allow positive amplitudes to be transmitted, then you have to add a DC level to your signal. All right, you have to add a DC level to your signal so that all the pulses are positive. All right, in this way, all pulses are positive. Okay, and that is for PM. But if your system actually can work on double polarity, then you can transmit this one as it is. Yeah. And of course, this one is for single polarity. Okay, this is, okay, I miss out A, B, and C. So you may want to fill it in. This is A. All right, this is B. And this is C. Okay, so now come to sampling. How do we actually perform the sampling in practice? All right, so there are 3 types of sampling that we can perform. The first one is called ideal sampling. The second one is called natural sampling, and the third one is called flat top sampling. All right, so it'll be easy to understand these 3 types of sampling techniques by referring to the diagram on your next slide here. Okay, so for ideal sampling, all right, we actually produce an impulse at each sampling instant. Okay, these are the impulses. All right, we generate an impulse at every sampling instance, like this. All right, and of course, again, the amplitude of the pulse correspond to the amplitude of the baseband signal that we are sampling. This is ideal. And the second type of sampling technique is called natural sampling. All right, in natural sampling, basically we produce pulses with short wave, and the amplitude actually is varying according to the amplitude of the signal that we are sampling. So in this case, you can see at the instant of sampling, the amplitude is this. All right, but because our pulse wave is of certain duration, therefore the width or the height of the pulse actually will actually change according to the height, the amplitude of the modulating signal. So you can see this amplitude is not constant. All right, this is called natural sampling. And then the flat top sampling, Flattop sampling basically is we perform sample at the instant of sampling, and then we hold the amplitude value. All right. So in this case, the amplitude of your pulse basically is corresponding to the amplitude of the modulating signal at the instant of sampling only. All right. The amplitude is only corresponding to the amplitude of the modulating signal at the instant of sampling. All right. So if the pulse or if the amplitude of the analog signal changes during this time, it will not be reflected in your pulses. All right. Your pulse will be a flat top one. So it's just taking the amplitude of the analog signal at the instant of sampling. So you have only one amplitude as far as your that pulse is concerned. Okay, so that is for flat top sampling. So there are three options, but again, by comparing these three options, we can see that as far as natural sampling is concerned, we actually seldom use it. Okay, because of recovery problem. Okay, why recovery problem? Because you see, if you use impulse, right, when we use impulse, the frequency of the sampled signal will be very, very high. Okay, and then they will have problem at the recovery later. In fact, generating also be a problem. How to generate an impulse of such a what do you call it? A narrow width. Okay, again, that is actually not easy to realize in practice. So ideal sampling is seldom used. Natural sampling, all right, because the amplitude of the pulse actually changes. Again, is not of a good choice because it's non-constant and therefore is actually susceptible to noise. Okay, and then it's also not easy to actually reconstruct this. So the third type, which is the more commonly used sampling method, is a flat top. All right. So we only read the amplitude of the analog signal or the modulating signal at the instant of sampling, and we hold it there. All right. And this is okay as long as our sampling frequency is high enough. All right. Then we can actually reconstruct or represent this signal quite correctly. Yeah. Okay. Then let's talk about how to realize the flat top sampling, how to implement the flat top sampling. So in order to do flat top sampling, we actually need a sample and hold circuit. All right, we need a sample and hold circuit. And this sample and hold circuit basically is quite simply constructed by using two FET transistor. All right. So we have one transistor G1, which is used for sampling. All right, and we have another transistor G2, which is used to discharge. All right, and our message is XT. All right, so this is our message, right? Our analog signal. And at the instant of sampling, when we want to perform sampling, all right, we need to turn on G1. All right, when you turn on G1, whatever voltage you have over here will be transferred to your drain, right, on this side, correct? And this voltage will charge up our capacitor over here. All right, the capacitor will actually charge up and then hold the voltage over here. All right, then we actually turn off G1. All right, as soon as the capacitor charged to the full voltage, or the voltage that represent the amplitude of our modulating signal, all right, we off G1. We turn off this transistor, then the capacitor will actually hold the charge and then maintain the voltage. Okay, then that will be for the duration of the pulse, how wide we want our pulse wave to be. Okay, and when we need to turn off our pulse, all right, so what do? We actually turn on G2. All right, turn on, once you turn on G2, capacitor will quickly discharge by this transistor here. Okay, when this is turned on, the charge on the capacitor will be discharged. And of course, you have to choose a correct capacitor value so that the charging and the discharging action is fast enough. Okay, and then it's off. Then the next time we want to sample again, all right, the next time we want to sample again, which is your KTS. All right, again, let's say this is 1 TS, and the next time we want to sample is 2 TS. All right, we turn on G1 again. We have to turn off G2. All right, we have to turn off G2 or else it's going to discharge. All right, we turn off G2 and then we turn on G1 so that whatever voltage appear across here at the XT, at the input to the G1 is transferred to the output of G1, which is from drain to source. All right. Again, this will charge up the capacitor quickly and form your second pulse. Okay. Then of course we off G1 and on G2 again. All right. We off G1 so the capacitor will hold the charge. Yeah. And then if we need to again, this will last as long as the duration of a pulse. Yeah. And then to turn it off, to turn off our pulse, so basically we turn on G2 so that the capacitor will discharge. Okay, and for this circuit or for this method to work well, you must make sure the pulse duration, which is tau, is very much shorter than our sampling period. Okay. So what that means, what is our sampling period? So your sampling period, of course, must be 1 over, that means 1 over TS is your sampling frequency, isn't it? And then your potential, again, your sampling frequency must be at least 2 times the maximum frequency in the signal that you are sampling. All right. So the equation for the pulses that we produce at the sample and hold circuit is given by this expression. All right. So basically, we take the sum, right, of all the value of xt at all the k value at the sampling instance. K is basically the instance of sampling. K can be 0, 1, 2, 3, 4, and all k's are all integers, and multiply with the pulse. Okay, and the equation, and this is a pulse where it's delayed accordingly. All right, you have pulses generated at all the k values. All right, and for all the sampling period again, the sampling duration. Okay, and then how does the pulse equation look like? The pulse equation basically again is to take the make sure we generate a rectangular pulse and convolve it with the delta function. Okay, and this delta function again need to give you a 1 at all the k values here. Okay. Method number 2. Okay, method number 2 involve convolution. All right. So what we did is actually we sample the signal using impulse sampling. All right, and then we convolve these samples with rectangular pulses. Okay, and again, if you look at the waveform on the right hand side, the first one is your baseband signal. Yeah, then the sample pulses basically again we have its height correspond to the amplitude of the baseband signal. And then the rectangular pulse, okay, is called HT. We have a rectangular pulse here, a very a rectangular pulse with a short pulse wave. All right, we actually convolve these two. All right, so when you convolve these two in the time domain, so what basically happen is you are reproducing a replica of your rectangular pulses at all the instances where the impulses are. All right, so therefore at every TS, NTS, you're going to have your rectangular pulse. All right, and the height of the rectangular pulse basically will correspond to the height of the impulses. Okay, so that is how the flat top samples can be produced by using method number 2. Okay, here this slide basically show you the time domain as well as the frequency domain representation of method number 2 flat top sampling. Okay, this is for time domain, this is for frequency domain. All right, how do I know? This is time, this is frequency. All right, so this is a time domain representation of the signal that we are going to sample. Okay, and the signal basically has a spectrum of this with the highest frequency at FM. All right, and then the sampled pulses. All right, sample pulses in time domain is our impulses. All right, so the frequency domain representation for impulses in time domain basically are also impulses in frequency domain, right? I believe you have learned this from the DSP, except that the interval, all right, the interval in time domain is T, whereas for frequency domain, the time domain is 1 over T, just because F is equals to 1 over T, isn't it? Okay. So now we multiply, of course, in time domain, when you perform impulse sampling, basically you are just multiplying these two signals. Yeah. So multiplying these two signals in time domain, actually what it means in frequency domain is we actually convolve them, right? We convolve these two. What that means is this baseband spectrum, all right, will be duplicated at every instance of sampling, right? So you have the frequency spectrum that is duplicated at every n over t. So this is 1 over t, this is 2 over t, this is 3 over t, and so on. All right. And now we are going to convolve with the rectangular pulse in time domain. All right, when we convolve this signal with a rectangular pulse in time domain, what it means in frequency domain is we're going to multiply the spectrum. All right, so rectangular pulse, the frequency spectrum of a rectangular pulse basically is sinc function, right? A sinc function, and then when we multiply these two, all right, the spectrum of sampled impulses with the frequency spectrum of a rectangular wave. So what you get here is you multiply these two. So what you get is now at baseband, you see the amplitude, the shape is still the same. The amplitude of your spectrum now at the centered at 0 frequency is the highest because of this sinc envelope. All right. And then your second spectrum here, the height will actually reduce because of the height here is less. Okay, and you're going to have another set here. All right, at all the again all the sampling n sampling frequency. Okay, so this will be again you're going to have multiple replica of the baseband spectrum. Okay, the shape and the shape and the amplitude actually follow the sinc function. Okay, so how to actually recover the signal later? All right, as you can see from the frequency spectrum, the signal can be easily recovered by using a low pass filter over here, isn't it? All right, and you actually because if you look at the spectrum of this signal, the amplitude is the highest here, so that means the component everything has is at its maximum value. What it should be, then therefore the recovery is actually the best at this point. All right, it doesn't mean that you cannot recover here. But here the amplitude is so low, where you want to recover here. Recovery here is easier. All right. So this will require a low pass filter only. All right. If you try to recover over here, you need a band pass filter. All right. So again, what we do is we recover it using a low pass filter. Okay. All right. So far, that's all for PAM generation. So we're going to move on to PAM demodulation. Okay, it's 12 o'clock. I think it's a good time to break, isn't it? Do you want a break?
Yes.
Okay, so let's take a 5 minutes break. And then after this, I'm going to continue with the PAM signal recovery. Do you have any questions so far?
Miss, may I not have you uploaded the notes to the Google Classroom?
I thought I have.
But I saw I didn't receive yet.
Let me see. I thought I did. No. Maybe I made a mistake. Oh, I didn't. Oh, sorry. Oh, I know why. Because I had trouble with Google Classroom the other day. Now, so many people are using Google Classroom. Sometimes, I don't know, I encounter more Google Classroom failure than what it used to be. I hope when we had our test and exam, the Google Classroom will be functioning as more normally, or else we'll have big trouble. Did you experience the first time when we had our assessment in Google Classroom and then we have Google Classroom was down for about half an hour?
Yes.
That was quite scary, isn't it?
Very panic on that day.
Oh yeah, I also panic that day. Wow, gabra only. Yeah, okay. Let me try. Okay, it's there. I remember I did over last weekend. I think I had problem. That's why it did not come up. I keep on getting black screen. Okay, tutorial. Let me see tutorial. Yeah, tutorial is there, but notes is not there. Okay. Lu Yao Ting asked a question. PW and PPM, which one less noise? Good question. What do you think?
I think PWM,
Why?
because PPM use pulse and the pulse only on for a while. If we didn't capture the pulse, then bye bye now.
PPM.
Ah.
That is about recovery, isn't it? Not so much about noise, isn't it?
Actually, I just
It's more
because
difficult to recover PPM signal as compared to PWN signal, yes, because if you don't capture the pulse, then it's gone. Yes, you're right. So that is one of the major requirement for recovery of a PPM signal is that you must synchronize. You must synchronize your pulse with at the receiver. You must make sure your pulses are synchronized to the pulses at the transmitter. Then you don't miss, or else you're going to miss. Yes, but in terms of noise, because noise are amplitude based, So noise are amplitude based. So again, for pulse width modulation technique, I think we discussed this after the break, yeah. Since some already went on break. Okay. What time do we come back? What time is it now? 12:04. Let's come back at 12:10, yeah. Okay, let's get back to our class. So, the question was what? PWM and PPM, which one less noise? All right. So the best way of let me get this down. All right, can you see my slides here?
Yes, Miss.
Okay, so in order to investigate the effect of noise, all right, on these three types of pulse modulated signal, all right, is by again, let's say I put in noise here, again, noise amplitude base, so it may change the amplitude of your signal in ppm, all right, and later when you recover, all right, let's say I have another noise here, negative noise, then therefore my amplitude will change, will be here, all right, and this one, my amplitude will be like this. So it will change the amplitude of my modulated signal. But what about pulse wave? All right, pulse wave, actually, it depends on where the noise is. If I have noise here, I'm not worried at all. All right, because the wave is still the same. Yeah, and normally our pulse height is our pulse height is actually quite high, so that the noise will not actually be so large that it can affect our the height of the pulse to, let's say, 0. You will not be able to reduce to 0. All right, normally noise, again, we talk about SNR, signal to noise ratio. All right, so normally the signal amplitude has to be much larger than the noise amplitude in the channel. So you can see if any noise riding on the amplitude, we're not worried because the width of the pulse is still the same. All right. However, if the noise, all right, if the noise were to appear here, let's say I have a positive noise here. All right, I have a positive noise here. Then you see that the width of my pulse will be wider over here. All right. So again, that actually depend on the recovery side where we measure our pulse wave. Okay, and what kind of height do we measure at what height, at what amplitude do we measure our pulse wave? Okay. And then for ppm again depend on where the noise is. If the noise come in here, we're not worried. Okay, but if the noise, let's say the noise come in here, all right, if the noise come in here, then my pulse will appear earlier than what it should be. All right, so again, your ppm will have wrong interpretation. Okay, that means the delay time is now shorter. The delay time is now shorter, and therefore the amplitude representation will be wrong. All right, and in this case, again, it depends on, so both cases depend on where the noise came in or when the noise came in. All right, and also this case it for PWN, it actually depend a lot on your amplitude of the noise. But in your ppm, yeah, if your noise happen here, then your what call it, the recovery definitely will be wrong. Yeah. So from this discussion, which one do you think is more susceptible to noise? PWM or ppm? But again, if you're for ppm, if your noise is here, you don't have problem because you're actually checking your delay time here only. All right, but if your noise appear here, then you have problem because your delay time is measured from the sampling point to the instant where you have your pulse. All right, so which one? If you really want to compare strictly, ppm is slightly worse in terms of noise immunity as compared to PWM. Yeah, agree? Do you agree?
Agree.
Okay. All right. So let's continue with our signal recovery. Yeah. So there are also two ways to recover the PAM signal. Okay. Again, because we generated the PAM signal using sample and hold, the recovery process can also be done using a sample and hold circuit, followed by a low pass filter. All right. And okay, let's take a look at this diagram on the right hand side. So we have a input, which is the PAM signals, and then this signal is amplified before we actually sample them. All right, normally PAM signal, when you arrive at the destination, the amplitude will be much lower, because of attenuation along the channel. So we need to amplify a bit before we sample them again. So we have a switch actually to perform the sampling. Okay, so when close the switch, all right, closing the switch, whatever GT will be, or in this case is our okay, this is GT. Sorry, I have to make some correction over here. This is GT, the signal coming in. This is a sample of GT. Okay, so the rectangular pulses are the sampled signal, are the sample signals that come in, the PAM signals that come in. All right, so when I close the switch, all right, when I close the switch, my UT here, okay, this is my UT. All right, my UT basically will actually read the amplitude of the sample signal. Okay, this pulse will read the amplitude of this pulse and then hold it. Okay, hold it, and the switch, it will hold it, and then the next time it sample again, you actually take the next amplitude of the next pulse. All right, after that you hold it again. So what you're going to have effectively, basically, is a staircase. Your UT basically is a staircase, like this. Right, that's what your UT is going to look like. And if you pass this staircase signal through a low pass filter, all right, then you'll be able to recover. Okay, again, low pass filter is to remove all the high frequency component, which is this sharp transition over here. All right, and then reproduce the original signal here. Okay, in this case, because this is high, right? Again, your original signal, again, you see UB may not be the exact representation. So in this case, it's going to look like this. All right. So you can see now on this side, this waveform are not the same. This is our original waveform at the transmitter. These are the pulses that represent this signal, but the one that we recover is actually this one over here. Okay, so there'll be some, in this case, you are not actually able to recover it exactly as it is. But again, if you actually read the samples, again, this is a sampling issue, all right? So you actually read the sample more frequently, all right? Or you increase the sampling frequency, then you should be able to reproduce the actual signal itself. Okay. All right, so again, as far as sampling is concerned, the sampling pulse train must be synchronized. So you have to synchronize our sampling, this switch. All right, how often this switch is open and closed need to be synchronized with the incoming PAM signal. All right, so that you read the pulse at the right time. And then for method number two, the issue will be the easiest. You just use a low pass filter. All right, as I showed you previously, if you look at the frequency spectrum of the PAM signal, you can actually recover it easily by using a low pass filter. Yeah, and of course, our low pass filter will not be ideal. So you may actually, your low pass filter response may look like this, right? Not. So if your low pass filter look like this, that means you're going to let some of this signal over here pass through your low pass filter. All right, and then you have to make correction here. All right, and the correction basically is by the use of the equalizer. All right, so equalizer, the use is actually to actually reduce the amplitude of the signal at the high frequency. All right, so that we actually recover the actual signal itself. All right, and this high frequency basically again is distortion, right? Because you actually recover this part, which is not your signal. Okay, so that is the two methods of PAM signal recovery. Of course, the low pass filter is the easiest. Okay, so I'm going to move on to talk about time division multiplexing. All right, time division multiplexing, as I mentioned previously, is basically used to combine, all right, combine several signals in time domain so that we can actually transmit them together over one channel. All right, because if you use one channel to transmit just one signal, it's kind of a waste of the bandwidth. All right, typically normally the bandwidth of a channel is quite wide, so you can use it to transmit more than one signal. Yeah, and then time division multiplexing is one way of combining. All right, as what is mentioned here is one way of combining several sampled signals. Okay, in a definite time sequence for you to transmit it over a channel. Right, we actually combine the signal. So in this case, we make use of a commutator. All right, commutator basically is to switch. All right, is to switch the samplers to different types of input, to different input signals. Yeah. This diagram at the bottom here basically show you the time multiplexing of 2 PAM signal. All right, we have 2 PAM signal. One is called F1T, the other one is called F2T. All right, and then we have a sampling circuit here. All right, sampling circuit here, and we have a low pass filter here. Yeah, this low pass filter basically is to limit the signal bandwidth, the sampled signal bandwidth, to match the bandwidth of the channel that we are transmitting. Yeah. All right, let's look at how it works here. As far as the sampler is concerned, we need to sample at a fixed interval, right? So this sampler is actually controlled. We have a pulse generator that generates pulses to perform the sampling or to provide the pulses. And then, of course, we have a clock that controls the frequency of the pulses, as well as the switching of the commutator between signal 1 and signal 2. All right, if you look at the graph on the right-hand side, all right, we have two sets of PAM. All right, the yellow color is the PAM signals for message number 1, and the black color is the PAM signal for message number 2. All right, and this is basically the output of a multiplexer circuits. So how we actually produce these sets of pulses is, okay, we actually start by sampling, by taking samples from F1. All right, we take samples from F1. So when the commutator is connected to F1, so this sampling circuit actually is reading PAM from F1. Okay, it's generating PAM signal from F1. So F1, the amplitude is here, all right, at the instant of sampling. Therefore, the PAM generator is this one here. All right, and then the commutator is switched to generate the PAM for signal number 2. All right, so the signal number 2, the amplitude is here. Therefore, the second PAM pulse actually come from signal number 2. The height is this. All right. Then the commutator is switched back to signal number 1. Signal number 1, the amplitude is here. So therefore, a pulse is generated with this amplitude. All right. With the commutator, then switch back to signal number 2. All right. Then signal number 2, the amplitude is here. So therefore, the PAM or the pulse height for signal number 2, all right, is this. All right. So that will actually give us a combination of pulses that come from signal number 1 and signal number 2. All right. So you can see as far as the signal that we transmitted in the channel, all right, this signal actually consists of PAM signal coming from 2 different sources. All right, one from signal number 1, the other one coming from signal number 2. Okay, so we can also combine more. All right, you just make your commutator switch faster so that you can actually sample all the signals before you come back to the first one. Yeah, so that is for TDM of 2 PAM signals. Any questions here before I proceed? No? And move on, yeah? Okay. So let's make some analysis here. So in this case, let's assume all input signal are low pass. So meaning they are baseband signal and then band limited to FM. That means the highest frequency component in both signals are FM. All right. And then let T be our sampling interval for one signal. And this T basically, again, is your Fs. All right. 1 over T will give you your Fs, your sampling rate. Yeah. So the T is your sampling duration for one signal. And that means this is your T. All right. I sample F2 at this instant. The next time I sample S2 again is at this instant. All right. So the interval between 2 samples for one signal is capital T. This is T. Yeah. And let N be the number of input PAM signals. In this case, we have 2. Our N is 2. We have 2 PAM signals. All right. Now let Tx be the time spacing between adjacent sample in the time multiplex signal waveform. So what is Tx? Tx is the time spacing between 2 adjacent samples. This is your Tx. All right. Adjacent sample means the 2 samples, one sample coming from signal number 1, the other sample coming from signal number 2. All right. So the time spacing between these 2 adjacent samples is Tx. All right. So Tx basically is given by T over N. Right? Because we have to sample between this time T, we have to sample 2 signal. Therefore, the spacing between 2 signal is just T over N. Tx is equal to T over N. Okay. And then, of course, you can see because the sample signal, the PM signal are actually rectangular in shape. All right. Therefore, the bandwidth, and then furthermore, we multiplex them, meaning we have more pulses now. All right. So the bandwidth of a time division multiplex signal actually is very wide. And it can go to infinity. Why infinity? Because of the rectangular pulses. All right. Now, how much bandwidth do we need then? Yeah, theoretically, of course, it's infinite, but in practice, nobody can have infinite bandwidth. So what is the necessary bandwidth for TDM signal transmission? All right, so again, for PAM, all right, for PAM, only the amplitude information is important, right? Yeah. So the absolute minimum bandwidth required such that the information in each sample channel remain independent of the other one is given by this. Okay, this is the bandwidth. is 1 over 2tx. All right, 1 over 2tx. And this is, again, you replacing tx with t over n. So your bandwidth basically is n over 2t. All right, n over 2t. And this has to be much larger than, or at least, you know, n fm. And what is fm? Fm, again, is the highest frequency in your modulating signal. All right, so with this equation, you can actually see that the PAM signal, all right, transmitting a PAM signal actually is very similar to the bandwidth required for single sideband AM. All right, because if you transmit, let's say I transmit only one PAM signal, then the bandwidth I require is just FM. Right, same as SFP, isn't it? Yeah. But if I were to perform time diffusion multiplexing, so that I transmit 5 sets of signals using PM, then your bandwidth would be 5 FM. Right, that is minimum. All right, minimum. And of course, in practice, you need more than that. Yeah, the minimum is again where our sampling, you know, our sampling is actually ideal. We're using impulse sampling and we use ideal filter. All right, and we know in practice, we can never have ideal filter. All right, and your impulse sampling, you will not be able to generate an impulse of a zero width and infinite height. Right, so again, in practice, your bandwidth is again larger than NFM. Okay, and also because we are using minimum bandwidth, all right, because we are using minimum bandwidth, therefore you can expect your pulses that you send will never be ideal or will never be a rectangular in shape. All right, will never be rectangular in shape. So the shape of your pulses will actually change according to the bandwidth that you actually transmit with. So your pulses, instead of a sharp transition like this, your pulses may look like this, you know, eventually. All right, so you look more sinusoidal rather than rectangular, a series of sinusoidal wave rather than rectangular wave. Okay, and in fact, it is not necessary to have a rectangular wave that you send, right? Because what you're interested for PAM, what you're interested is the amplitude, right? So you always take the amplitude at the recovery side. You just take the amplitude of every pulse that you receive, then you should be able to recover it. Yeah. Okay. But if you actually need to recognize the pulse, you need to maintain the rectangular pulse, then you definitely need much wider bandwidth. All right. That was what the last statement is about. Okay. All right. So what about receiver? All right. We combine several PM signals together. We transmit it over a channel. And at the receiver, how do we actually recover each signal respectively? All right. So again, at the receiver, we need to perform sampling again. All right. The resample, and then we separate them into the appropriate channel or appropriate signal. Yeah. Now, if you look at this circuit at the bottom, again, we need a clock. All right, this clock again need to be in the same frequency and also same phase as the clock we use at the transmitter. Okay, so that we can recover the incoming multiplex PAM signal accordingly. All right, so again, we do sample again, and then this clock again control this commutator. All right, we read the first sample, and this first sample actually belong to signal number 1. So we pass to the low pass filter of signal number 1 to recover signal number 1 here. This is a low pass filter number 1. All right, and then to recover signal number 2, which is the next sample coming in, right? Again, the commutator now switch to the circuit for signal number 2 recovery, which is a second low pass filter. All right, and then in order to recover signal number 2. All right, so again, for you to work correctly, as I mentioned just now, the clock and the commutator must be synchronized again. Okay, that is for recovery. And then when we have many PAM signals that you TDM together, all right, if you do that, then the width of the pulses will be very narrow, isn't it? Isn't it? Because for the same duration, all right, let's take about this. All right, let's say for the same duration over here. Where is my pen? Oh, here. Let's say the same duration. Let's say from here to here, I only sample 2 signal. I sample 2 signal. Right. So my pulse width can be very wide. Right. But with the same duration, I need to sample more signal. Then my pulse width have to be very narrow, isn't it? So that I can sample more. All right. So when your pulse widths are narrow, all right, that means your signal power will be very, very small. Right, your signal power basically is equal to the not only the amplitude, right, also the duration of the pulse, isn't it? So because of the width is now getting narrower, now our output signal power is going to be very small as well. Yeah. Therefore, for this kind of circuit, you definitely need to have an amplifier to amplify the signal that is coming in. All right, or you actually use a different sample and hold circuit that can actually hold the amplitude. All right, which means let's say I'm going to take the sample for message number 1 here, like this. All right, so my sample and hold circuit now is going to sample the same amplitude. All right, and then hold it so that it lasts longer. All right, so when the pulse lasts longer, so what happens is the power of the pulse or the signal actually will be more. All right, again, that will make it easier for you to recover your signal. Okay, again, by using low pass filtering methods. Okay, right, so this slide actually will show you how, I think it's the same as the one I talked about previously, yeah, the sample and hold for recovery. So again, we make use of a switch. All right, and the switch here is this switch here. Okay, so this switch here is turned on and off in order to sample the signal at the instant of sampling. All right, and then you have a resistor in series. So this resistor in series basically is to again, if you combine with the capacitor over here, all right, it's actually to charge up the voltage or the value, the signal at this point. All right, so they hold the same voltage as the incoming one. Yeah, so your RC must be very small as compared to your pulse duration. All right, so you charge up fast. But then when the switch is open, because the next pulse does not belong to this in this circuit, so the next pulse they belong to another circuit because it's another message. The message is not meant for this circuit. The message is meant for the next circuit. Then the switch will be off, isn't it? So when the switch is off, then of course your capacitor now will discharge through this R over here. So this R again, in order to hold the voltage level of the output, the RC value has to be quite large. Okay, and of course it needs to be much larger than the sample duration. T is your sample, the duration between 2 samples of the same signal, and tau basically is the pulse duration. Okay. So again, with the input PAM signal like this, okay, again, this is the PAM signal for this circuit. All right, in between, you may have PAM signal for another circuit, which you don't want to read. All right. So what you need to have again, your this switch, all right, will turn on at time t, all right, last for a very short duration, and then after turn off, then turn on again at the next time t, okay, for every nt. So this is t, 2t, 3t, 4t, and so on. Okay, so the output again will be a staircase, right? Because we sample and hold, so the output will be a staircase like this. All right, and then if you were to pass this staircase signal through a low pass filter, then the low pass filter, of course, will block the high frequency component, right? So basically, this sharp transition here is your high frequency component, isn't it? So you smoothen it. All right, you smoothen the sharp transition and reproduce your output signal. All right, again, there's the analog signal, the more gradual waveform. It's no more staircase. Okay. All right, let's talk about the advantages of TDM. So as far as TDM is concerned, the switching, the sampling, everything was done using digital circuits. Therefore, as far as TDM technique is concerned, is reliable. All right, it's also efficient. Yeah, and then compared to FDM, in FDM, basically you need to combine the signals using a different carrier frequency. Right, basically you need to modulate every individual signal using different carrier frequency before you combine them. All right, so as far as FDM is concerned, you need many carrier frequency component, and you need many mixer, right, or multiplier in order to generate the in order to bring every signal to different carrier frequency before you combine them. Whereas for TDM, you just need to make use of the commutator. All right, you switch between the signals, and then you can just straight away share them over the channel. All right. So as far as the circuit is concerned, the TDM requires simpler circuits, right? And then for FDM also, right? If you recall the FDM from the previous chapters, is that when you need to recover the signal, basically you need to you need to multiply the income signal with different carrier frequency, and then you need to have a different filter for each and every one of them. Yeah. So therefore, as far as TDM is concerned, the circuit is actually a lot simpler. Yeah. And when the inputs are of similar bandwidth, then the TDM can multiplex many channels of low frequency data very efficiently. All right. Okay, then compared to FDM, the interchannel crosstalk, all right, arising from nonlinearity of the amplifier is actually relatively small. All right, because we are actually using a lower frequency as compared to FDM. TDM basically works on a low frequency as compared to FDM. All right. So again, we know amplifier does not perform very well, especially at high frequency. Therefore, as far as TDM is concerned, the performance is much better. And what are the disadvantages of TDM then? Okay, again, because TDM depend a lot on your sampling pulses. All right. So therefore, the accuracy of the pulse that you generate is very important. All right. And also, if the pulse is not generated at the right time and lasts for the right duration, then it will give you a timing jitter. All right, timing jitter. Again, these are problems that happen only at high frequencies. All right, these two problem will actually be a problem at high frequency. Yeah, so therefore, TDM normally works at the lower clock frequency, which is about below 100 megahertz. All right, below 100 megahertz. But for FDM, it can work as high as you want. Okay, it can work at a lot higher, much higher frequency than we want. So for FDM, it's not a problem. So whenever you need to multiplex signal and then transmit at high frequency, very high frequency, you definitely need to use FDM. Yeah. But for lower frequency transmission, TDM is good enough. Yeah. And there's additional requirement, right? You have to make sure that the transmitter and the receiver pulses are actually accurately synchronized for you to recover. Yeah. Or else if you miss the pulse, then you miss the information already. Okay, this slide, okay, complicate the issue a bit, where we actually can, you see, just now I was talking about PM signal, right? PM signal as it is, you cannot transmit it wirelessly. So therefore, it's mainly used for short distance transmission with cable only, right? And if you combine TDM, use TDM to combine them, again, it's also over wired and over cable. Yeah. But if you want to transmit the PAM information wirelessly, okay, especially over long distance, all right, then you have to modulate. Okay, you have to perform modulation already. Yeah. And this is called continuous wave modulation. Basically, it's analog modulation. All right. And then the purpose of this again is to translate our PAM spectrum to higher frequency so that you can transmit wirelessly. All right. So how to do this? You can actually do it two ways. One is using AM. The other one is maybe AM followed by FM. All right. So what we can do is here we have a PAM multiplexer where we combine several PAM signals together. All right. After that, we perform amplitude modulation on the combined signal. All right. And this example basically is just a double sideband suppressed carrier modulation, isn't it? Because we make use of a carrier component here. All right. Of course, you can also use double sideband full carrier. And then you transmit wirelessly, yeah, over the radio channel. Then at the receiver, receive the signal because it's amplitude modulated. So therefore, you need to perform demodulation. All right. And then followed by the PMD multiplexer. So now you have to split the signals. Because here you combine the signal. Now you need to split the signal. Okay. And again, to split the signal, you need the clock. Yeah. And of course, to demodulate the signal using AM method, again, because we are using double sideband suppressed carrier here, therefore you need a carrier component at the receiver in order to recover your signal, right? And then for even higher frequency transmission, right, in this case here, this is an example where we actually combine two sets of TDM signal. So here we have one PAM multiplexer to give you one set of TDM signal over here. And we also have another set of PAM multiplexer that give you second set of PAM signals. All right. So these two sets of PAM signal are actually used to modulate different carrier. This is carrier, not clearly. This is carrier number one, let's say. Carrier frequency number one, and this say carrier frequency number two. All right, these two are using different carrier frequency. Therefore, it's going to occupy different spectrum, right? Okay, different frequency center at different frequency. If we were to add these two together and we again perform frequency modulation on the sum of these two AM signal, then we can transmit them again through antenna. Again, this will be a higher frequency, all right? As far as FM is concerned, it will be about 100 megahertz and so on, right? Is it 100? Yeah, 100 plus megahertz. Okay, but if you transmit using AM, you can only transmit at what? Highest is about 1.6 megahertz only, isn't it? All right, this one you can transmit 100 plus megahertz. Okay, so that is a short explanation or description on how we actually transmit TDM signal wirelessly over long distance. Okay, I have about 7 minutes left. Shall I proceed or shall I continue? Let me think. Is it okay if I proceed? I just quickly go through the rest of the slides. All right, so the next few slides basically cover PWM and PPM. All right, I actually put more emphasis on PAM because PAM is the one that is going to lead us to the next chapter. All right, whereas PWM are just some pulse modulation techniques that you need to be aware of. All right, so as far as pulse width modulation, or some books call it pulse duration modulation. Right, pulse duration modulation. As I mentioned previously, when the signal amplitude is high, the pulse width is wide. Right, signal amplitude is low, the pulse width is narrow. All right, and then how we recover it? Recover it again by using low pass filtering. Okay. And where do we apply it? The application basically is, I think you learned about PWM before, isn't it? Yeah, PWM before. PWM. One of the application is to actually digitally create an analog output voltage for control function and power supply. All right, especially when you control the speed of a motor. All right, control the speed of a motor, we use PWM. All right, we can also using PWM to digitally create analog signals for any waveform that you like, sound, speech, music, and so on. All right, again, these are just electronic sound, I would say. Okay, the problem with PWM. PWM, the problem is the pulses are varying width. Okay, the width of the pulses are changing according to the amplitude of the baseband signal, and therefore the power content is also changing. All right, so there is no way for us to know the exact power of the PM signal. And then for PPM, the pulse position modulation, where the pulse amplitude and width are constant. All right, where the position of the pulse actually depend on the amplitude of the modulating signal. All right, to recover this PPM signal, basically you need synchronizing pulse. All right, you need to send synchronizing pulse to the receiver so that the receiver know when is the starting point of a pulse. Right, because if you don't know the starting point of a pulse or sampling time, you need to know the sampling time. All right, in order you need to know this so that you can calculate the pulse delay time. All right, so therefore you need to send the synchronizing pulse to the receiver. Okay, how PDM and PPM pulses are generated. These two type of pulses can be generated using a comparator. All right, with a sawtooth generator that generate triangular pulses. Right, so PDM basically will be the output of the comparator. All right, so let's take a look at what happened here. You know how a comparator works, right? Yeah, we connect the signal, the modulating signal or message signal, to the positive terminal of a comparator, and the output of a sawtooth generator. This is the output of a sawtooth generator, which is a sawtooth waveform. All right, we actually connect it to the negative input terminal of the comparator. Okay, so as far as comparator circuit is concerned, when the positive terminal input is more than the negative terminal, then a positive output is produced over here, right? Right or not? When your positive terminal input is more than the negative terminal input, then you have a positive output. All right. Otherwise, meaning if it's smaller, then your output will be 0. Okay. So now if you actually compare these two signals, okay, this is my XC is this one, red color. Okay, so if you actually look at the output of the comparator, right? At this point, your XT is it more or less than your the triangular waveform or the sawtooth waveform? It's more, isn't it? The amplitude of your XT is more than the amplitude of the sawtooth waveform. Therefore, a positive output is generated. All right. And as long as XT amplitude is more than the amplitude of a sawtooth, right, you have a constant positive output until this point. Right, until this point where XT amplitude is less than the sawtooth amplitude now is bigger already. Then the output now becomes 0. Okay, so it stays at 0 until the next time the XT amplitude is more than the sawtooth again. So it go up, there will be positive output from the comparator and then stay positive until your XT is become less than the sawtooth. All right. So it will be like that. And then the next time, now your XT is, okay, can be more, can be less, but you look at the next instant, your XT now is more than the sawtooth. All right. Therefore, you have a positive output and last as long as your XT is more than the sawtooth, okay, which is here. So you have this pulse wave modulated waveform. All right. And then to generate PPM, is to send the PDM signal through a monostable circuit. All right. So this monostable circuit again will be triggered at this mono circuit will be triggered at the negative transition of the input. All right. So when the input goes low, the monostable will produce a pulse. Yeah. Okay. So the next time the input goes low again, it will produce another pulse. All right. That's how a mono circuit works, isn't it? Monostable circuit works, right? So this again, so after you have generated PDM, to generate PPM actually is easy. So depending on which signal you want to transmit, you want to transmit PDM, then you just send it as it is. But if you want to transmit PPM, you send the PDM signal through a monostable, and that will give you your PPM. Okay. Okay. There are problems with the pulse modulated signal. All right. The pulse modulated signal, as mentioned previously, it was mainly used for short distance transmission. All right. It was mainly used for short distance communication, and you have to use cable. All right. And then as far as PAM is concerned, you have a problem with noise. All right. And then for PWM, you may have distortion on the pulse shape, right? As I mentioned before, if you have a noise at the beginning of a pulse or at the end of a pulse, that may change the width of the pulse, all right? And therefore, your output will be distorted as well. And then PPM, of course, PPM is not easy to recover. It may be easy to generate, yeah, because you just make use of a PWM with a monostable, but to recover is not easy because you need a synchronizing signal from the transmitter. So actually, as far as pulse modulation signal is concerned, again, as I mentioned previously, just to trace, it's only for short distance, low noise channel. All right, and it must be a wired channel. All right. So, and then the one that is actually used nowadays, yeah, we actually use PCM already. All right. Again, PCM is also for wired channel. All right, we're going to study PCM in the next chapter. All right. So as far as PCM is concerned, I believe you have learned this PCM in your, I think, some of your previous courses. Right. So instead of sending pulses with the amplitude of different values, we actually send pulses with only two amplitude, either a positive amplitude or no amplitude. All right, ones or zeros. All right. In this case, our pulses will be of equal height and equal shape, easily to recognize at the receiver. Right. So as far as the receiver is concerned, when you use PCM, the receiver just to know whether is there a pulse or is there no pulse. All right. And then to do that, of course, to actually just send 1 and 0, we need to do is we actually need to convert. We need to convert our amplitude, all right, into a form that can be represented by a binary coding. All right. Therefore, we need to perform A to D conversion already. Yeah. So next chapter, I'm going to cover this. Yeah. Even though the pulse will be distorted, but then you can still see whether is there a pulse or is there no pulse. All right. So the recovery process will actually be much easier. Okay. So this will be what we're going to learn in next chapter. Okay. I overrun a little bit already. Okay. So you can actually go through everything yourself after the class. Right, and I will, okay, I have class on the other end. I will have class on the other end, so I have to stop now. And if you have any question, then I will answer them in our next class later on. Is that okay?
Okay, Miss.
All right, okay. Make sure you prepare for your test on Wednesday. Can send us the past year. What is that? Past year or not? What is past year or not? Past year question Past year question you can get from the library Hey, learn how to access the library past year question bank and then get from there. Yeah. Okay. All right. If you're able to do the past year exam question, the midterm test question will be like kacang already. Okay. All right. So, okay, I have to go now. All right. See you on Wednesday. Yeah. Bye-bye.
Bye bye. Thank you, Miss.
Bye.